In the previous video, we considered the double-slit experiment, and starting from some assumptions, we were able to compute the probability amplitude for the system. In particular, this was the somewhat complicated expression, but actually this is something that's not too complicated because we even implemented this probability amplitude in MATLAB, and the numbers that we plugged into the equation were the following. So in particular, we chose the width of the slit, which we called delta, or the same as sigma. If you remember, sigma appeared in the amplitude or also in the probability density that we started from. So this was the initial assumption for the probability density. This is not the only possibility, as I said in the previous video, and of course different probability amplitudes, different probability densities would lead to different amplitudes, and therefore you might have a different calculation. And I mean, the important thing though is to consider the basic phenomena behind this mathematics, and the basic phenomenon is related to the interference pattern that you have in the double slit experiment. So here in this video I want to show you some more tangible physics behind these equations. So I want to do some more considerations, and I also want to show you the resemblance between what we did here, which is seemingly more difficult mathematics than usually taught in books describing the double slit experiment, but I actually want to show you that there is a resemblance and that there is a connection between what we did here and what you see in ordinary, let's say, physics books. So, as I said, let me start describing what we did last time. I mean, the choices that we made last time regarding the double slit experiment. So we chose delta to be the width of the slit, and remember that we had two slits along some x-axis, and the two slits had the same shape, the same I mean, yes, the same shape. So the width delta is the same for both slits, and the probability density or the probability amplitude, whatever you want to call it, as a peak at the center of the slit. You have to think this delta is quite small, but the mathematics that we did were last time were quite general, so you could consider in principle even larger deltas, because our formulas consider a generic delta actually. And here you have a similar function which contains a peak centered at the center of the slit. And therefore it means that we have a 50% probability, more or less, that we find the particle at this slit, and another 50% to find the particle at the center of this other slit. Right? So this is quite intuitive, but we are still considering quantum mechanics because we are considering wave functions, and then in the previous video we carried out the calculation by means of path integrals. So this is some kind of advanced way of looking at this experiment, at this problem, but it is a very general way that contains lots of powerful insights and physics. So I think that this is quite interesting. It's a very interesting point of view. So as I said, this delta, we chose it to be of the order of 3 times 10 to the minus 5 meters. Then we have this capital delta. Capital delta is simply the distance between the centers of the slits. So this is capital delta, and capital delta is greater than this lowercase delta. So this also explains the choice of the notation that I used in the previous video. So this is capital delta because it's larger than this lowercase delta. So you can remember that in this way. Then we have TF. If you recall, So here we have the two slits, and then we have some screen or wall, whatever you want to call it, at a certain distance with respect to the y-axis. So here we have some yf coordinate, and the particle, if for example the particle goes through this slit, it will move in some way, and then it will reach this screen. And this screen is reached after a certain amount of time, tf, elapses. And that amount of time, we chose it to be 10 to the minus 2 seconds. Then we chose the mass of the particle, and if you recall, we chose the mass of the particle to be the particle of the, to be the mass of the electron. So 9 times 10 to the minus 31 kilograms is the mass of the electron. Then we have the Planck constant, the reduced Planck constant, which is the usual very small value, 10 to the minus 34 joules per second. And then we also chose the location of the two slits for convenience and for symmetry reasons. So we chose the first slit, the one on the left, to be located at minus delta, capital delta over 2. Remember that this capital delta is 10 to the minus 3, so we already have a number here. And the other one is symmetric with respect to the origin. We have some origin here in the middle, and then we have the same distance between the origin and the two slits, if you want. Now, I want to show you what happens if we increase the mass of the particle. So instead of having an electron, for example, let's assume that we have some particle which is much more is much heavier than the electron. For example, 9 times 10 to the minus 3 is of the order of some grams. And this is something that we expect to behave in a classical manner, right? So let's see what happens if I run this script. If I run the script, you can see that we don't have any interference pattern because we only have two very narrow peaks located at the centers of the slits. So the maximum that we have on the left is located at minus delta over 2. And minus delta over 2 in this case is something like minus 5 times 10 to the minus 4. Because remember that delta is 10 to the minus 3, if I remember correctly. Yes. And of course, the other maximum is symmetrical, but in the positive orientation of the x-axis. So you can see that we don't have any interference, and this is a very classical behavior. But if I restore the mass of the electron, remember that this is what we got last time. So we got this interference pattern that's reminiscent of the quantum weirdness that we witness when we discussed the double slit experiment. Now, this is not the only thing that I want to show you in this video. So I want to show you something more, something that can be related to what you see usually in books, because this is something that I developed myself. So this is not my invention, right? Because the physics is there, it is available to everyone, but this is not something that I have taken from books. It is something original that I wanted to show you. So it is my way of explaining the double slit experiment to people who are already aware of the power of path integrals and quantum mechanics in general. And now I want to show you some simple mathematics. So there is nothing difficult in this lecture. There is no path integral, just a bit of algebra and some simple geometry to show you that indeed we can connect what we did last time to what you see in physics books. So first, let me remind you what these two parameters were, a and b. In particular, this parameter a, you can see that it appears in these exponentials. So these are real exponentials. A is a negative number because you see that you have this minus and then you have a positive quantity here. So A tells you how fast these exponentials will decay. So it has its own very simple, intuitive interpretation. It's not difficult. Whereas B is related to the frequency of oscillation of this sinusoidal function here. So we will be interested in this B, and for the sake of convenience, I want to reason in the following fashion. In particular, I want to consider delta to be very small. Remember that delta is the width of the slit, so it's as if we are considering the slit to be infinitesimally uh, small. So this aperture, this gap, this opening, whatever you want to call it, is very small. And if delta is very small, remember that delta is equal to sigma, according to what we did the last time, and to our considerations. Basically, this delta is related to the standard deviation of this Gaussian function here, which is something quite intuitive if you think about it, but never mind. This sigma is very small. So if sigma is very small, we have this term in the denominator, which we assume that to be non-zero, but this will be larger than something that is very small, and therefore we can say that, let me do it here, this implies that A is approximately zero. So we can consider A to be very small, very close to zero, and this simply means in this case that these exponentials are very close to 1, because if A is very close to 0, of course, the exponential is very close to 1. But what we will be interested in actually is B. So B, in this case where sigma is very small, can be approximated by the following expression. So B is approximately equal to 1 divided by 2h bar Tf divided by the mass of the particle, right? Because if this is negligible, then you have this one in the numerator, but we have the square of that in the denominator, therefore we can write B like this, or if you want, like this, m divided by 2h bar Tf. Simple as that. And so far, so good. There is nothing too important about this. But if we introduce the momentum of the particle, so let's call it P, we have the momentum of the particle. So we assume that our particle is moving with a certain velocity that I call V, and if we multiply the velocity of the particle by the mass of the particle, we get its momentum. Simple as that. So we assume that we can consider just classical physics. I mean, and when I say classical in this case, I really mean the physics that's far away from relativistic consideration. So there is no relativistic behavior that we have to consider. We only consider the usual standard Newtonian physics for this particle. So the particle has a momentum p, and then it can be written as the mass of the particle times the velocity of the particle. So we can rewrite b in terms of momentum, because we have the mass here, which is equal to P divided by m. So we have P divided by 2h bar Tf multiplied by V. And let me put these two together. So what is Tf times V? So V is the velocity of the particle, and Tf, as I said, is the time taken by the particle to reach the screen beyond the plate with the two slits. So Tf times V, well, it is something like the space traveled by the particle to reach the screen or the wall, whatever you want to call it, and we can call that just like d. So this would be d. It is some distance equal to Tf times v. Now, if we sketch our system, here we have the plate with the two slits. Remember that these slits are very small, and we assume that the wall, which is located at a distance yf, and let me also remind you that here we have the distance between the two slits, which is delta. Now we assume that yf is much larger than this capital delta, right? And what does this mean? This simply means that, for example, if we consider this to be, let's take this one. If we consider this to be the point on the screen where we have the possibility, for example, that we travel from here to reach the point, or we travel from this slit to reach the point. What this assumption tells us is that basically, since delta is very small with respect to yf, it means that these two lines are basically parallel to each other, okay? And it's as if I can consider, for example, this point, the middle between the two slits. So it's as if the particle can be considered as starting from here until it reaches this point. And this is not really difficult to understand. For example, so let's assume that we have this path first, and we consider this to be straight lines for convenience. So, for example, if we consider this path, and we call this the path number 2, whereas this is the path number 1. This is slit number 1, and this is slit number 2. So you can understand the numbering there. So the path traveled by the particle moving through the slit number 1 is this one, and it would be TF, which is the same, because remember that in our considerations we consider the same TF, and this is independent of whether we pass through the slit number 2 or slit number 1. We have to multiply that by the velocity of the particle here. Since this path number 1 is longer than the path number 2, it means that the velocity that we have along this path 1 is larger than the velocity that we have along the path 2. And if we square this, which is this distance, we can calculate it. We can calculate that quite easily, because this point is located at a distance which, if you recall, according to the notation that we used the last time, this was xf. This is the final point. I mean, this is the x-coordinate of the final point. So if we consider that, we can simply use the Pythagorean theorem. So the distance that we have here would be xf plus capital delta over 2 squared, because remember that this distance here is delta over 2 in absolute value. So if you consider the x-coordinate, it would be minus delta over 2, because it would be a negative coordinate, but in absolute value, it's delta over 2. And then, of course, the y-coordinate is simply yf squared. And similarly, along the path number 2, we have tf times b2 squared. This would be xf minus delta over 2. If you consider the second path, you still have this delta over 2. But in this case, you have a subtraction, because you are interested in this length, which is xf minus delta over 2. And still here you have yf squared. So since, as I said earlier, this delta is much smaller than yf, it's as if we can consider just a velocity v, and here I multiply by tf and I square it, and I can neglect writing down, I can neglect this delta, so I can avoid writing down delta. I can simply write xf squared plus yf squared. Simple as that. And now if I introduce an angle with respect to the vertical line, so for example, now what I showed you is that I can simply consider this path according to this assumption here. And I want to describe now the angle that this path forms with the vertical line that I have in here. And the distance traveled at this point, this distance d, is simply the length of this red path, right? So xf squared plus yf squared is also equal to d squared. Simple as that. And for example, we can write xf as this length d times the sine of the angle theta, whereas yf would simply be d times the cosine of theta. Now, if this theta, this angle theta here is small, and this would be the case if yf is very large, because if yf is very large, if we keep xf fixed, of course theta has to decrease. So if theta is quite small, the sine would be approximately equal to the angle theta, and of course the cosine would be approximately equal to 1 up to first order. And at this point, remember that we defined b like this. And I want to rewrite now this function, this formula in a different manner. So remember that h bar is equal to h divided by 2 pi, where h is the Planck constant, whereas h bar is the reduced Planck constant. So here I get a factor of 2 pi, and then I have 2h times d. And if I introduce the wavelength lambda, the wavelength lambda can be written as h divided by p. And therefore, here we have p divided by h, so it means that this can be written as 2 pi divided by 2 lambda times d, like this. And remember that this b appears inside the sinusoidal function, inside this sinusoidal term. So if we want to consider the maxima, so the positions of the maxima, and when I say maxima, I mean the maxima of this probability amplitude. Those maxima would occur when the sign here is equal to -1, because here we have a minus. Therefore, if this sign is equal to -1, we can maximize this probability. So it's like choosing the xf such that it maximizes this probability. Remember that these exponentials are very close to 1 because we have chosen a to be very, very small by choosing the width of the slit. So there is no dependence on xf here because the exponentials are considered to be 1 according to the simplifications that we considered. So now remember that this x tilde 1 was equal to minus delta over 2. So if you set x1 equal to minus delta over 2, with this minus, this will become a plus delta over 2. So when you multiply delta over 2 by minus 2 delta, you get minus delta squared, which it will cancel this delta squared. So you will be left with b, which multiplies minus 2 delta xf. And this would minimize, in this case, this sinusoidal function, because we want the minimum of this sign, because the minimum multiplied by minus will become a plus 1, right? So we want the minimum of the sign, and that occurs when this thing here is equal to minus pi over 2 plus or minus 2 pi, and then we have some integers. So I'm considering, for example, positive integers, and with a plus or minus they can be also negative integers or whatever. Remember the expression that we have found for b, which is this one. So this can also be simplified. It is just pi divided by lambda d. So pi divided by lambda d, and then this is multiplied by minus 2 delta xf. And so we can also rewrite it as minus 2 pi times delta xf divided by lambda times d. And now also remember that there is a dependence between xf and d, because we found that xf is approximately equal to d times theta. So this means that xf divided by d is approximately equal to theta. And remember that we set it equal to minus pi over 2 plus or minus 2 pi n. And therefore, here, if we divide by minus 2 pi, we get delta theta divided by lambda equal to 1 over 4 minus plus or minus, this is not really important, n. And we can also multiply by lambda. And this is a result that is very similar to what you see usually on books, because on books, in physics books that describe the double slit experiment, you exactly have some formulas like this. So you have the distance between the slits multiplied by the angle that we defined earlier is equal to some integer, and I will explain in a moment why we also have this factor of, sorry, this term 1 over 4, but n is an integer, and then we multiply that by the wavelength the wavelength associated with the particle. But the maxima usually are written in this form. If you check books, you have something like plus or minus n lambda without the term 1 over 4. So why do we see this 1 over 4? This is not a mistake, actually, because this is due to the choice that we made in the previous video for the probability density, P, which led to this probability amplitude, and in particular this factor of I here, because so we chose this probability density, but in principle we might have made other choices, and these factors are just some constants that serve to normalize the probability, but never mind. But this I is not really necessary, it is not mandatory. We might have chosen other phases, because remember that this is associated to e to the I pi over 2, so it's like a phase of pi over 2, which is reminiscent of some phase difference between the amplitude that you have on one slit at one slit and the amplitude that you have at the other slit. But in principle, you might have chosen also a function that does not contain this factor of I. So you have the same phase between these two functions. Of course, then the normalization constants would be different, and the square of such an amplitude would give rise to a slightly different probability there. But actually, what I want to show you is that what I want to discuss is indeed the fact that this factor I is not really mandatory. And the calculation would be exactly the same or very similar. The only difference would occur when you calculate the square of psi, the mod squared of psi. You can see that that phase factor appears in here, right? So here we add a cosine. But if we set this phase factor to this phase factor to 0 instead of pi over 2, then instead of having the minus sign in here, you would have the cosine plus cosine. So instead of having minus the sign of blah 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 b times all the rest, you have the cosine of this. The argument inside the sinusoid would be the same. And therefore, in that case, if we want to maximize the cosine, we don't have to set this expression equal to this, but rather we have to set it equal to just plus or minus 2 pi n, right? And in that case, if you do the calculation, you don't get this term of 1 over 4. So you simply get this expression here, which is the expression that appears in books describing the double slit experiment. So that's what I wanted to show you. I wanted to show you that the mathematics that we did in the previous video lead to very precise results, which are very general, but if you do also some simplifications, you can see that what we did agrees with what you see normally in books, and that's basically it.